Good morning, everyone. Firstly, I haven't even answered. First, I'd like to thank the BBRF for the opportunity to come speak to you on this award. It's a great honour, and also thank you to John for nominating me for this as well. So you've heard a few really nice talks this morning, focused on epidemiology in people and also on mice and how they can behave. So we're going to kind of do a bit of a mix here. I work in humans and rodents. So I'm going to, I suppose, take you through some preliminary data and hope to show you that potentially we can use decision-making tasks and processes to look at the underlying brain dysfunction that we associate with psychosis and why I think this is beneficial. And I'm also going to sort of give you a tutorial on how we can look as a behavioral neuroscientist at decision-making. We make a lot of choices that are quite simple at that moment, but behind all that is a lot of processes and background computation that our brain's doing to get us to that choice. And animals do it too, and we can use that to our advantage, I think. So this is what I'm interested in, translational research. The term's been used a few times this morning, but what I'm referring to is looking in rodents, mice, and humans in parallel, the same tests run side by side, so that the data we get from patient groups, we can feed into the experiments we're doing in rodents, and vice versa, then unpicking that circuitry in rodents to understand more about what's happening in patients. So essentially, using animal models to complement and expand our knowledge of human disorders. And this is important because we can learn a lot more about the brain in a mouse. We have better tools, we can do more invasive things. And that gives us an idea of what neurobiology is underlying altered behavior. And we need to know that for drug discovery. We can't fix a problem we don't understand. We can throw things at it and it might work, but it's not really the best way forward. However, there are simple ways to do this, but one of the sort of the difficult things in mental illness research, and especially in schizophrenia, which I'm interested in, is how do we measure psychosis in a mouse? They don't get psychosis as far as we can tell. So this is kind of the dilemma we face, and this is what I'm trying to deal with here and trying to find a solution to. So a lot of people know what psychosis is in general. It's a group of symptoms that's sort of a distortion of reality in the mind of perception. And the obvious ones are hallucinations, which have been brought up this morning, auditory primarily in schizophrenia, but also visual, seeing things that aren't there, and delusions, so paranoia, conspiracy theories, these false beliefs that you can't be budged. And for a psychiatrist, it'd be quite simple to tell if someone has psychosis. You can ask them questions about, are you seeing things, are you hearing things, how are you experiencing life, ask their family, because they might know stories about them. It works quite well. Mice, not so much, yeah. Interviews don't really work, they're pretty stubborn. So what can we do? We have to think of other ways to approach this problem. So what do we know about psychosis that we can use to look at in mice? We know that dopamine, which is a neurotransmitter in the brain, is linked very highly to psychosis in a lot of individuals with schizophrenia. We know this because drugs that induce dopamine release, like amphetamines, induce psychotic symptoms in healthy individuals, and they exacerbate those same symptoms in patients. We also know that all the antipsychotics we have block dopamine signaling to some extent. So we can push and pull this neurotransmitter system, and the symptoms follow on with it. Now, I'm going to give you a little bit of neuroanatomy here, but bear with me, I'll keep it simple. This is if you took a section of the head through here, took a slice of the brain, and kind of looked at it. And in one of the part of the brain will look like this. It's a mirror image, two hemispheres. And this is what we call the striatum. This is probably the densest part of the brain where dopamine signaling occurs. And I would draw your attention to these color divisions. Here we have a primate or a human and a rodent, pretty similar. The different colors here are the different functional subunits. So the orange here is what we call the mesolimbic striatum. And it's kind of involved in the motivational reward processing. And then the yellow, which is the area I'm interested in, is called the associative striatum. And it's called that because all the cortical areas come in, and it's important for integrating that information and help us make decisions. And the blue is the sensory motors. Once a behavior becomes habitual, you don't have to think about it so much. Generally, this region is involved. Now, what's important about this division is that we now know that some of the dopamine dysfunction we see in schizophrenia is not located throughout the brain. It's specific to some subregions. And a lot of work has gone into showing, a lot of clinical work has gone into showing that it's the associative striatum where the increase in dopamine we associate with psychosis is located. So you can see here, this increase here in patients versus controls. And this is just one measure. There's a variety of measures they can use. These are in living people. They're testing them as they're sitting there in a machine to show that dopamine is increased in the associative striatum, but not in the ventral striatum. Now, one of the problems is our animal modeling has always thought that the ventral striatum was where this problem was. So all our tests to sort of mimic psychotic-like behavior have been looking at ventral striatal-based behaviors. So this is a problem. We're maybe not looking at the right thing. However, this also presents an opportunity for us to now use this new knowledge and think, well, what can the associative striatum teach us about this same thing? And can we harness that for preclinical research in animal models? So the first question is, well, what could we test that would be sensitive to dysfunction in this brain region? And there's a few different processes. I've mentioned decision-making a few times. Obviously, that's my thing. So one of these decision-making tasks we can use is about goal-directed behavior, our ability to modify our actions to chase goals, something that's more valuable. And there's also another, which is behavioral flexibility, our ability to rapidly change with changing strategies and environmental rule changes on the fly, become very flexible. So I'm going to walk you through two tasks, one that tests each of these that we do in humans and mice, and show you why I think they're useful. So the first question, and this is where the preliminary data is going to come in, is does manipulating dopamine systems in a mouse reproduce the deficits we observe in psychosis? Sort of test number one, right? We need to show this first as a point. Is this even worth following up? So for goal-directed behavior, I use a task called outcome-specific devaluation. A lot of strange words, but it's a very simple task. Essentially, we train humans and mice to associate two actions with two outcomes. So left and right on the joystick for humans, and left and right levers for the mice, so I can press those. And for humans, they get a token. Here the example's a star or a circle, and it's worth credit, so they get money at the end of the test. Everyone likes money, so that's good. With mice, they don't care about money. We have to give them some food, so we give them a food reward, so they work for the food. So once they've learned these associations, and they know left is this, right is that, what we do is we devalue one of these outcomes. So for the human, we'll say, okay, the star is no longer worth as much money. For mice, what we do is feed them to satiety with one of these outcomes. It's kind of like eating a lot of steak. You'll still eat the ice cream, but you don't want any more steak. So we can just devalue the one food item. And then we put them back in this environment where they've got these two choices, and we say, okay, what do you want? Respond accordingly. And what you see in healthy individuals is this bias in responding. So they'll respond more for the outcome that was not devalued and less for the devalued outcome. We see the same in mice. So collaborators of mine in Australia have shown in schizophrenia patients this behavior is impaired. And this is their data here. So this is a preference ratio, and I'll use these graphs in my work coming up. So the higher this bar, the more they responded for that specific outcome. And you can see healthy adults respond much more for the valued item than the devalued item, as you would expect. Whereas in patients with schizophrenia, they respond pretty equally across the board. So they're not updating their actions according to these changing reward variables. They're making poor decisions in this task. So we had to change the task, because in Queensland we couldn't use the same protocol as they did in New South Wales, which I can talk to you about afterwards if you like, but that's just science for you. So in my hands, what do we see in psychosis? So as I said, this is preliminary results. The story may change, but I want to walk you through why I think it's useful. So firstly, we see that in healthy adults, we see a very nice preference ratio, as expected. It's not that difficult, except for this one person. There's always one. So as we look through the other test groups, the different patient groups, and we're expanding this to look at, as we said, schizophrenia is quite heterogeneous. So there's a lot of different groups we can look at. And I'm going to focus on early psychosis and schizophrenia, persistent schizophrenia here. What we see is that in early psychosis, there's a limited number here, but very strong response. And we see that start to disappear with schizophrenia. Although it's a lot of variability here. There's a lot of schizophrenia patients that show quite good bias here. So, maybe what's the difference between those groups? We're not sure. That's what we're going to look into. But there's a clear difference between that bias between this valued and devalued outcomes. So it fits what we know with a disorder that other people have done. And we're interested in following this up. So now, okay, let's go back to mice. What happens if we give them amphetamine to stimulate dopamine during this task? And we don't give them amphetamine the whole time. This is work done by my Ph.D. student, Kinacon. What we do is we give them amphetamine during the learning of the left and right, the training. During the devaluation, the choice phase, there's no drug, so they can make their choice uninhibited from a drug consequence. And what we see is mice can do this task too. That's good. So saline-treated mice, these are healthy mice, show a nice bias towards a valued lever. And whereas with mice that have been treated with amphetamine, we see this dose-dependent decrease in responding until it's flat. This is only a moderate dose. They're not just running around not knowing what's going on, they're responding fine. And you can see it just knocks it down and it's flat here, like we see in schizophrenia patients in the other studies, and I suppose this is more like the data I showed you before, it's going to go in that direction. So this suggests that increased dopamine, what we associate with psychosis, can also impair decision-making in a cognitive task, which is nice for this idea. So both schizophrenia and dopamine can impair the ability to integrate changes in reward value, so when something changes, do we change accordingly, and modify the action selection accordingly. So that's the first task. So the second task, let's go back to walking through a behavioral test. So behavioral flexibility, and the test I use for this is called serial reversal learning. And again, it's quite simple, but we can dive a bit deeper into this task, and I'm going to walk you through it quite slowly. So we give people two pictures. Here are the examples, a triangle and a circle. And one of them, if you select it, is going to give you more rewards than the other one. Okay, so it seems pretty straightforward. Same with the rodent, except it's a left and right lever again. So what we do is once someone learns that this, say the triangle here, the plus, is more rewarding than the other, without telling them, we just switch it. So now the circle's the best option. And they have to keep doing this, selecting and selecting until they establish that, wait a minute, this is no longer very good, and I'm going to go to the other one. And then when they get good at that one, we switch it back. And we switch it back and forth, back and forth, back and forth. So they have to navigate this change over and over and over. And we use different circuitry for this in our brain. We can make it easy. We call this deterministic. Every time you select the correct one, you get a reward. Good job. Every time you don't get anything. Very easy. We'd all do it very easily, and we couldn't really get much data from it because we'd be too good at it. So what we do is we make it probabilistic. If you select the correct stimulus, you'll only get a reward 80% of the time, say. And conversely, if you select the incorrect stimulus, we're going to reward you occasionally just to throw you off. So this is misleading feedback. It requires different use of strategies to complete this task. And that's where it gets interesting. So it's not necessarily how well you do at this task, but it's how you approach it and how you do it. So I'm going to walk you through a hypothetical so you can keep up with me when we get to the data slides. Let's say you selected a triangle. A 1 being you won, a 0 being you lost. What do you do next? Do you select the triangle again, or do you select a square? So there's multiple ways we could go about this. If you won on the triangle, and you selected a triangle again, we call that a win stay. Makes sense. Triangle's good. I like them. They keep giving me rewards. I'm earning more money. However, if you lost on the triangle, you might go, no, I don't like triangles anymore. I'm going to switch to squares, because I prefer them, because this triangle's no good. So they're the two primary strategies we use. In a deterministic task, that's the only two you'd need to use. But when we make it probabilistic, we also get these other options. You might win on a triangle. There we go. You might win on a triangle and decide to shift anyway to a square. Because you're a nice try triangle, I know you're not actually better overall. The square is more valuable if I keep selecting it. And you could also lose stay. So even though you don't win on the triangle, you know it's better overall. Just this one loss isn't enough to change your mind. You're going to stick with it. I still like triangles. So these are our 4 strategies. And we can look at these strategies to really look in detail at how animals and people make their decisions in this task. So now I've told you about these strategies. Are they different? What do we see in those with psychosis? What we see, this is a win, stay, lose, shift bias. So a higher value on this graph means that person tends to win, stay, and lose shift more than win, shift, and lose, stay. Yes. Essentially use the primary strategies more so. And what we see here is that the patients with early psychosis tend to have a lower bias here. They tend to use those strategies less. There might be a little decrease in the schizophrenia patients as well, but it's quite obvious in the early psychosis. So is this because of the win, stay, or the lose, shift? So we can split that up. What we see is it's clearly because of a decrease in the lose, shift. So early psychosis patients tend to stay with a stimulus even if it loses. They lose stay more often. They're less likely to move away from it. Right? So when we did the same task in mice, how does increased dopamine affect this choice? So with increasing, oh, that's gone too far, sorry. Sneak peek ahead. There we go. When we increase dopamine, we're using the same dose of amphetamine used before, 1 mg/kg. We see a similar decrease in this win, stay, lose, shift bias. When we split this up, it's not as obvious as in the early psychosis patients. There is a slight decrease there potentially, but it may be a bit more, a few other things going on. So let's delve deeper. What can we ask ourselves? If you were to lose stay more often, what would we expect you to do when a switch happens? We'd expect that you might get stuck. Even though you start losing on this stimulus, you might just keep with it for a bit longer. And we call this perseveration. So how many errors you make by picking that used to be correct stimulus that's now incorrect. How long do you keep picking it until you're willing to explore and switch that other one? And what we see is what we'd expect with the early psychosis patients, an increase in these errors because they're lose staying. They're sticking with that stimulus for a bit longer, a little more stubborn and fixed in that. And we also see the same in our mice when we increase dopamine function. So this is all mapping on quite nicely. And we could close the shop here and say, okay, it must be that increased dopamine is making these changes in early psychosis patients, and it's a really nice story. But I don't like to stop there. We need more information. Why are they staying more? What's causing this? And we can't extract this from the data in the sort of conventional ways. What we do is we use, is it going to switch? Computational modelling. We can use algorithms, and I don't write these algorithms, I borrow them from other people. We can use algorithms that will look at every trial-by-trial basis and at the history of trials and sort of impute some of the way the person's making choices. And it can tell us a lot of cool things. It tells us there's more emphasis placed on wins or losses. You might purely make your decisions based off winning or by losing, for example. We can look at, is it the last trial that was the most important? Or are you building a case over a series of trials before you make a choice? We can also look at exploring, which is kind of random sampling. I haven't chosen this one in a while. I don't know how it's going to go. I'm just going to test it anyway, even though I don't think it's better. Or exploit, which is very straightforward. This one's better. I'm sticking with it until I know it's not correct. So we can pull a lot of different values out of these tasks with this computational modeling. And it can tell us more about what's going on underlying these processes. So we've applied some of these to these data sets. I'm going to talk to you about just some of these, rewards and losses here. So these is a reward learning versus loss learning. And underlying what we saw before in the early psychosis, it seems to be that it's driven by this loss, a decrease in this loss learning. These are arbitrary numbers. What this means in real world is that people with early psychosis are putting more weight on the past losses. So these recent losses they accumulate when they switch don't mean as much in the context of their overall choice strategy. So they get stuck in it a bit longer, so it makes some sense. And this is where things get interesting and complicated, but that's how it's meant to be. If it was simple, we'd already know the answers. We see a different pattern with the mice. So even though we see the same behavioral phenotype and profile, it's probably more likely driven by differences in reward learning. So this is the same sort of a decrease in this value means more weight on past wins. So again, when the switch happens and they start losing, they're still emphasizing the past wins, which means they get stuck on it. So what we see is the same behavioral phenotype, but driven by slightly different processes that underlie that. I think this is why it's important to look in detail at these behaviors and really extract all the information you can from them. So behavioral flexibility in psychosis. Shown that early psychosis and dopamine can alter decision-making strategies. But underlying mechanisms may still be different. There's a bit of lag on this switch, sorry about that. So in summary, psychostimulant exposure in mice can reproduce multiple aspects of cognitive dysfunction that we see in psychosis. And obviously more work needs to be done in this space, but this may be a way we can look at psychotic neurobiology using a cognitive task that we can use in both mice and humans. And the stage of illness may be critical. It seemed to map better on with schizophrenia in the outcome devaluation task, but early psychosis in the seroreversal learning. So there's obviously a lot more going on here. We have to take into fact antipsychotic exposure, chronicity of illness as well. So the ongoing work in this space, as is, I'm a young scientist, this is all still moving forward, and this is what the BBRF award is going to help me support and continue on, is what you saw from Christoph's talk before, manipulating some of these circuits with these viral manipulations. So we're going to tease apart some of these circuits in the associative stratum that control these behaviors. So what do we have to move to see a difference in loss learning? So what do we have to turn off or turn on to see that difference in loss learning? We're also pairing this with functional brain imaging in people doing these tasks. So we can see which areas of the brain are active or inactive during these same stages of the task. And that will help guide our viral manipulations in mice. So I hope if you take something away from this talk is that we can do some really cool stuff with behavior in both mice and humans, and that there might be potential for applications that we can use to benefit both cognitive dysfunction in schizophrenia as well as psychosis, because we're treating the same substrate. We just need to have better models that we can test these things on. And nothing's done in a silo. Obviously, I work with humans and mice. That means you need people who have psychiatrists and can recruit, and also people who know how to work in mice. So you need twice as many people. So thank you to everyone here, and thank you for listening.
Great presentation. Questions? Yeah, well, I have one. I always thought that amphetamines increase goal-directed behavior and focus and all that, and yet your research and your colleagues' research seems to demonstrate the opposite. I wonder if you can comment on that.
So you would have maybe noticed with some of those graphs that the lower dose of amphetamine seemed to improve performance. This is kind of what with ADHD, right? A little bit of dopamine can help someone with ADHD focus and improve their cognitive function. So a lot of these neurotransmitter systems, you've got to have the right amount. You can't have too little or too much, and they can both cause problems. So for some people, you may need to bump dopamine up a little to improve performance. In other people, they're already at the top end, and if you give them any more, it's going to knock them over the edge. So it's an optimal dosing in that level, yeah.
So if you go way too much?
You just get psychosis, pretty much.
Got it. Okay. Yes. Dr. Brown?
Thanks for a great talk, James. So my question is, have you looked at any correlations between their performance on these tests and their cognitive profile? And especially when you point out about perseveration and things of that nature, or even looking by subtyping of different cognitive abilities, schizophrenia cases, or even going beyond that to positive, negative symptoms.
So we run these studies, the two tasks, these were all the same people who did both tasks. And we run them in line with IQ tests as well, and a PANSS assessment. So that data is still incoming. That's the idea. I suppose IQ is not a very good cognitive measure necessarily, but at least it gives us some yardstick to have a look at. But I am very interested in looking at the symptom profile of these patients and how they perform.
Yeah, and also, for example, tests, and I don't know how well it would correlate, but things like working memory, set shifting, more specific cognitive tests. Do you think there's value in that, or is that not?
Yeah, I'd love to do all the tests I can, but we try to keep this pretty simple. So this whole run in a control participant, a healthy adult, takes less than an hour. So we find that people are very amenable to doing it. We can recruit very highly, so the numbers are coming in quite fast. So you got to pick and choose. So in future, yeah, I love attentional set shifting. I've done it in mice before, not in humans yet. But yeah, I'd like to include more. So this is I suppose the first pipeline towards that.
Yes, ma'am.
I guess I'm wondering, what are the implications for cognitive remediation? I guess it's just, you're looking more forward, and how you could use the findings to help people who are already diagnosed and have these cognitive distortions or difficulties.
Yeah, good question. I suppose I'm sort of thinking from the basic pipeline is drug testing and treatment options that we can use to test in mice and then get to people. But I know that there's a lot of apps and brain apps that people are using in patients to give them something to do, and that can be useful. And I suppose one avenue for this might be incorporating some of this learning type strategy into that, whether it would be a training or more ability to get more data from people and see if they improve or worsen over time. How that would work, I'm not sure. But yeah, the cognitive behavioral therapy is hard to do in mice. So it's...
Yes, sir.
Hi. Much of the phenotype you describe seems to disappear between early psychosis and schizophrenia. What are your thoughts about that?
Yeah, so, well, one, antipsychotic exposure. We always hear about how it doesn't fix anything, but potentially it might not help some things too. So we got some interesting results I didn't show about also adding some antipsychotics to these behaviors with the mice, and it doesn't show what we expected. It's more complicated than we thought. It doesn't necessarily reflect what we see in patients either, but I think chronicity of illness and early psychosis hasn't necessarily been fully diagnosed at that point. I know that the work from Bernard's lab that I showed, where there was a complete knockout of that behavior, was on an average age 45 years in a patient. So we don't recruit above 50 for my study, so our patients are a bit younger. So I wonder if age has a factor to do with that. Maybe it's a deterioration due to age, but as we build numbers, yeah, it was a bit interesting to see that they seem to perform quite well in the reversal learning task when we know that generally that's impaired in schizophrenia.